assignment. Well, welcome back. So I think we have, next week is the last lecture, right? So we only have a couple of lectures left. So before we begin, a couple of quick administrative things. So one is about the assignment 3 extension. So I saw a lot of discussion going on in Piazza. Like some people saying I should have extended, some people saying I should not have extended. And apart from whatever you see in Piazza, there were also a lot of email requests. So given the fact that everybody is overloaded at the last minute and the acrocritic assignment was a mistake, we extended the deadline by a few days. Now, there was some comment in Piazza about like we should give bonus to people who submitted on time. Okay. But if I go by that argument, like then it doesn't make sense to extend the deadline at all. Like the goal is not to punish people who submitted late. Like there were a lot of people struggling to submit. So we gave some time for them to finish it. Like, so if you finished it on time, like then move on to the next project, right? Like, so like you have a project deadline coming up soon. So like, so you have saved some time for doing the project, like while others are still working on their assignment. So I think we will not give any bonus for people who submitted on time, but overall, like, so I have asked the TAs to be very, very lenient with the third assignment grading, given the fact that there were a lot of like issues during the assignment. So you can expect very generous grading for A3. Okay, so that's the solution. Okay, and other than that, you should have received an email about details of like for the final exam. Like, so I know that a lot of you are not from Poly and you don't check your Moodle announcements regularly. So, or you don't get an email from the Moodle announcement because it goes to your Poly email ID, which you never use. So if so, please go check the Moodle for the announcements. Like, so it has all the details about the final exam. Okay, so, but probably there is one thing that I did not mention in the email, like which is, I don't know how many of you have done open book exams before. So there's a lot of undergrads in the class. Like, so if you have never done like open book exam before, so please don't think that open book is a substitute for not like preparing, like for preparing for the exam. Okay, so if you think you have access to all the notes, so you can prepare your answers on the fly during the exam, you cannot finish even half of the exam. Okay, so the exam time is not for you to search for an answer in your notes. So you have the notes to like help you, like, so when you're coming up with your answers. Okay, so the answers are not there in the notes or online. Okay, so given the fact that it is open book, it is also a lot of work for me. Like, so I have to set questions which you cannot Google directly. So don't waste your time in Googling or like trying to find answers. Then you're going to lose your time and you will not finish the exam on time. Okay, so that doesn't mean exam was long. So I don't want complaints later saying, okay, the exam was very long. If it was long, probably because you spent a lot of time searching for answers. Okay, so prepare as if it's a closed book exam. Like, so do all your preparation sincerely and use your lecture notes to help you like write your answers better. Okay, so let's get back to the lecture. So where did we stop last week? So we looked at hierarchical reinforcement learning, right? Like, so like we talked about how like learning a policy or even planning with low dimensional space is a very complex thing to do. Like, so, and how can you simplify things if you have a higher level abstraction? But then it is not that easy to simplify those things because learning those higher level abstractions is one of the open problems. Okay, so but we just touched upon like the challenges and like some basic algorithms like in the previous week lecture. The goal was really to introduce you to hierarchical order, like not to explain in detail like so the state of the art, right? Like, so in the similar spirit, like, so today we are going to talk about a couple of real life challenges that you could face when you want to let's say implement any of the algorithms, traditional algorithms that we have learned in this course so far, right? Like so the first we will talk about partial observability. Okay, so what if the agent cannot see the entire world at once, right? Like so then like things like Markovian assumption doesn't hold anymore, right? Like so like how do I act from the current state, like say if I don't have access to the entire state, right? Like so we're going to talk about that in the first half of the lecture. And for the rest of the lecture, like so we will talk about the idea of offline reinforcement learning, like so, which is learning a policy without any interaction. Okay, now why is that desired, right? Like so maybe there are safety critical applications where interacting with the world is very difficult, and maybe there are like situations where you can interact, but the interaction is costly. Okay, so then you want to make use of the data that you have, right? Like so we will talk about more motivations like when you get into offline model, but the general idea is like, so how can you learn a policy while you cannot interact with the world, right? Like so on the other hand, for the whole course, like so what we have seen is like algorithms that learn by interaction, right? Like so now how can we extend those algorithms to this offline setting? So that is what we will talk about in the second half. Okay, so let's get started. Well, like as usual, like if you're wondering where are the lecture notes, like we don't have the lecture notes like for this lecture. Like it was yet another extremely busy week, but I will be releasing the references and the scribbles. Okay, so but this is going to be a very high level lecture, like so like you should be able to follow like even if there is no lecture. Okay, so now first let's talk about partial observability. So we posed the problem of reinforcement learning in a Markovian decision process framework, right? Like so we have this MDP framework, okay, where the basic idea is you should be able to make predictions about the next state just from the current state. Like you don't need the history, right? Like so in other words, the probability of ST plus 1 given S0, S1 to ST, okay, is same as the probability of ST plus 1 given ST. So if this condition is satisfied, then like we just have this Markovian states, like so where things are much nicer, right? Like so we can do value iteration, policy iteration, or any other fancy algorithms that we have seen in this course. Now, if we look at the causal graph of this MDP, okay, so this is how it would be. Like so you have some state ST, okay, and you take some action AT. Right? Now this state and action takes you to the next state, right? So the next state ST plus 1 is caused by just the current state and the action that you took in the current state. So there is no dependency with the previous states, right? Like, and also this gives you the reward RT plus 1. Is that right? So now with such a Markovian setup, like the entire transition dynamics can be captured with just one matrix, right? Like so let us call that matrix as P. So you have this Pij of A, which is the ith row jth column entry in this matrix, okay, like for taking action A, which is nothing but the probability of ST plus 1 is equal to Sj, given ST is equal to Si, and AT is equal to A. Is that clear? And we also like there is also an unsaid stationarity assumption here. Like, so we make an assumption that the transition dynamics of the world doesn't change over time. So like that's why you can represent it with just one matrix, right? Like, so otherwise, like it has to be temporally conditioned as well. Okay. Now this transition function can be summarized by the T function, okay, which we have seen previously, right? Like, so this captures like the probability of transitioning from S to S dash, given that I took action A at S dash, right? Like, so this is basically the same as the previous one. So probability of ST plus 1 is equal to S, given ST is equal to S and AT is equal to A. So these are just different notations, like for the same thing. Like, so we are going to use these when we talk about extending MDP. Okay. Now, so this is the basic MDP, like where everything is observed, in the sense when I have a state, the state comprises all the information that I want to take the optimal action, right? Now, when you don't have that luxury of seeing the entire state, right? Like, so now how do we deal with such partially observed states, right? Like, so now we can actually extend this MDP framework to what is known as partially observable MDP. Okay, now this is a generalization of MDPs in which the states are not fully observed. Now, before I define partially observable MDPs more formally, let's look at a similar causal graph. Okay, so like, so where to understand like what is the dynamics of the world in a partially observable setting. Now, even if you observe the world partially, if you think about what is happening in the background, right? Like, so there is actually a state, like so the environment has a state. It is just that you don't see that state. Like, so you see only part of it, right? So in the back, there is an MDP which is operating, but you don't have access to that MDP directly. Okay. So if you go by that assumption, like, so you have the usual MDP, which is operating in the back, so which takes the current state and the action, okay, to give the next state. And also the next reward. Okay, so this is the underlying MDP. However, as an agent, like when you are observing the world, you're going to see some part of the world. Okay, so given the underlying state, okay, there's going to be a function which, given ST plus 1 and AT, okay, will give us some OT plus 1, okay, which is the observation. This is the state. This is the observation. Okay. Now, so if you think about what is visible to the agent, so this part is completely hidden. Okay. So agent only sees observation, and it takes an action, and that results in another observation. Now the agent has to take action in this observation and so on. So the agent does not have access to the state space. Is that clear? Any questions? Okay, so now we can actually formalize this whole thing. Like, so now let O, scripted O, be a set of observations that the agent can receive. Okay, now in the case of MDP, okay, so POMDP is a generalization of MDP. Okay, so you can also pose MDP as a POMDP with the only with one simple modification, that like, so you will just assume that O is equal to yes. Okay, so MDP is a POMDP where like state is equal to the observation. Okay, just remove this. Okay, now let O be the set of observations. Okay, now we need some way to model this arrow, right? Like, so we need a function which takes the given state and gives us some observation. Okay, so we're going to call that as some Z function. Okay, so well, some papers would also call this as I function, influence function. Okay, so it like the letter doesn't matter. Like, so this function basically takes a state and action. Okay, and it gives you a distribution over the observations. Okay, now similar to the T function, the transition function, which is operating in the state, we can talk about Z function, which is given by S dash O A O dash. Okay, now this function is the probability that OT plus 1 is equal to O dash. Okay, given ST plus 1 is equal to S dash and AT is equal to A. Is that clear? Okay. Okay, so now I can define a POMDP as a tuple which has S, which is a set of all possible states of the underlying MDP. Okay, A, which is your action space, T, which is the transition dynamics of your underlying MDP. Okay, and you have R, which is the reward function. Okay, so this until now, like this is the usual MDP. Now we are also going to add a set of state observations, O, and the Z function. Is that clear? So far I have only defined a POMDP. So now we need to talk about like how to learn a policy, like when you have just observations, right? Like, and how do you update your knowledge about the state and so on. Okay, so let's do that. So to do that, like we are going to talk about like how different trajectories like can be modeled, like both in the MDP setting and like POMDP setting. Okay, so now in the case of POMDP, okay, so our history is going to be all the states, observations, and actions until my current timestamp. Okay, so my history is going to be something like this. Like this is the complete history. So it's going to be S0O. Okay, so S0O0 A0. Okay, then S1O1 A1 to ST OT AT. Okay, now this is the complete history in the sense it has both states and observations. Okay, now we are going to call a set of all such complete histories as, let's say, H. This is a set of all complete histories. Okay, now if you think about the underlying MDP, like which is what you are trying to learn, that doesn't care about the observations, right? So the underlying system or the system that is operating in the background is going to have its own history, which is what is going to be used for computing the reward function. Okay, so now that history, let us just call that a system history. Okay, and we're going to call this as H. Yes. Okay, so this system history is going to have just the states and actions. Like, so the first state and action, then you go to the next state and you take some action there, and you go to the next state and you take some action there. Is that clear? Now this is the history that actually matters for computing the reward function. Like, so and every processing that is happening in the back, right? Like so. However, the agent is going to have a different history. So the agent is going to see the observation history. So observation history, let's just call that as HO. Okay. Now this HO is going to be a bunch of actions and observations. Okay. Now there is a small shift here. So it's going to be something like this. Okay. Because the agent actually in the beginning doesn't know what state it is in. Okay. So it will have some belief over what state it is in. Okay. Let us just call that as B0. Now, based on this belief, the agent is going to take some action. Okay. So that is A0. So that action will result in an observation. That action will result in observation, and then like you take an action and so on. Okay, so I think there is a question in the chat. Okay, I'll answer the questions about exam towards the end, but let me take the question about POMDPs. Okay, can you please give me a practical example between observations and state? And in what scenarios do we have partial observability? Well, I think, okay, so okay, I will come to that question very soon. Okay, so is this clear? Like, so the agent is seeing this trajectory. Okay, however, the system has this trajectory. And in fact, your value functions are based on the system history. This is system's history, right? Like, so your value is basically defined from the system history to some real value. So your value function is defined based on the system's history, but you are acting in the observation history. So there is a mismatch here, which needs to be handled. Okay. Now, before I continue, so there was one question in the chat about what are the practical situations where you would have partial observability. Like, in fact, there are a lot of practical situations. Like most of the practical, like interesting problems that we want to tackle has partial observability. Okay, like if you think about the original grid world, like simple grid world examples that we have seen so far, right? Like so, like we made this assumption in these grid worlds that the agent can actually see the entire grid. So that is why it knows which state number it is in. Like, so let's say this is a 36 state grid, right? Like, so how did the agent know that it was actually here? It's because it has the view of this entire world, right? Like, so now I can take the same grid world, but make it a 3D grid world. Okay. Now the agent is a physical robot. A physical robot which is standing here, let us say a robot which is standing here facing upward has a limited view, right? So it can only see what is here. So it cannot see what is here, or what is here, right? So at that particular time step, it can only see in the front. Like, of course, in the next time step, it can move and see the nearby things and integrate information. Okay. However, for that particular time step, it has a limited view, right? Like, so now any robotics task, this is going to be the case. Like, so you have a limited view. Now, also think about self-driving cars, right? Like, so if you want to design a reinforcement learning agent for self-driving cars, like now the agent only has the view which is in front of it, right? So it doesn't have the view of the complete map and like what is happening before or after, right? Like, so for most of the real life applications, like you cannot have a complete state. So in which case you have partial observability. So, okay, now let's get back to our POMDP formulation. Yeah.
So given like the observation history, if you all have this entire observation history, can you accurately decode always that which state you are in, or are there any scenarios where even though you have the complete history, you still cannot figure it out where you are?
Okay, so that's a good question. The question is like, given the observational history, can you figure out which state you are in? So answer for most of the cases is no, because the Z function with some non-zero probability is giving you like any possible observation, right? Like, so just by observing something, like you cannot say whether it came from state 1 or state 10. So it is very difficult. And in fact, like we have a lot of nice guarantees with MDPs, right? Like, so with POMDPs, like you don't have much of those guarantees. Like, so it is very difficult to learn optimal policies or exact solutions in POMDPs.
That function doesn't like take into account the entire observation. Just take one thing.
That is true, but I can give you a practical example. Like, so for example, let us say like we have a robot to access this entire building, right? So the state is really the entire building. Now, at any point of time, the agent might be in one room, right? Like, so it can of course move around and integrate as much information as it wants, but there is always some changes, right? Like, and also like the world is so huge that like you cannot capture everything. But there is also another philosophical question here, like, so do we really need to know the complete state of the world to take an action, right? Like, so for most of the actions, partial observability is enough, right? Like, so for example, let us say like I'm in this room, like, and I want to take an action here, like, so it doesn't matter what is happening in like the nearby rooms or outside, right? Like, so for most of the situations, it is context dependent, like so like you can take actions by looking at the context, even though this context is not a complete state. But there are places where like this could hurt you, like so which means you need to think about modeling the uncertainty. So like the crux of partially observable problems is there is uncertainty, right? Like, so you don't know which state you are in. Now you have to make decisions under uncertainty, right? Like, so now how do we make decisions under uncertainty? Like, so we are going to resort to probabilistic techniques. Like, so we will see how to like set up belief distribution over the states and update our belief continuously so that as we do more and more interactions, it gets better. Like, and like we have a decent idea of like which state we are in. So, but I think it is, I'm not sure if it is possible to extremely decode, like exactly decode the state.
I have a question.
Yeah.
So when we want to have an accurate representation in such scenarios, so do we try to with the observation, do we try to kind of based on the observations we extend and make a proper we estimate the states which we have not seen also, or we just take an action based on the observations we have?
Well, you can do both, right? Like some algorithms would, like that's what we're going to talk about now. Like some algorithms would directly learn a mapping from O to A, but some algorithms would have a mapping from O to S, like with some belief representations, and then from S to A. Okay, so both are possible. Okay, but in general, okay, so the idea here is you have a trajectory which is basically a bunch of actions. Okay, so like I'm converting the notations on the fly from the nodes, like so it's superscript in the nodes, like we are using subscript in the course. Okay, so okay, now given this history, let's say at time t, okay, now the goal is to learn some action AT, okay, which is just a function of HT. that clear? So we want a policy which will take the current history. Now, remember that it is not enough to just take the current observation, like so, because like it is not sufficient to take an optimal action. Now, I can give you another example, like so, like where you don't need to you don't need to decode the complete state. Okay, so like let's take most of the Atari games, like so. Now, if you're playing a game like Pong or Breakout, okay. Now, if you just look at one frame, okay, so now let's say these are two players and the ball is here. Okay, so this is you and this is some other opponent. Okay, now I give you just this frame, which is my current observation. So can you tell me whether I should move up or down? No. However, instead of just giving you this one frame, I give you a couple of frames from the past. Okay, so this is a time t. I also tell you that at time t minus 1, it was like this. Okay, so now can you tell me if I should move left or right? Sorry, up or down? So what should I do in this case? So this is t minus 1, this is t. So should I, okay, maybe I'll put a different color. So this is us. Okay. So should the agent move up or down?
Just a little bit.
Little bit up.
Little bit up. Why? Okay, is the ball coming up or down? The ball is coming down, so you need to adjust. Okay, so okay, maybe I drew it badly. Like maybe I'll just change it to something like this. Okay. So now the previous time step it was here and it just moved a little bit here, right? Like so now the ball is coming this way, so probably I just need to adjust it like based on that, right? So now here is an example of partial observability. Like if you just look at one frame, but you look at a couple of frames put together, then you have an MDP, almost MDP. Okay, so this is one of the reasons why, like if you look at deep Q networks that play Atari games, so they would stack the previous 4 frames. Okay, because when you stack the previous 4 frames, you can, to a reasonable extent, guess the direction, speed of like whatever objects that are moving. Okay, so then it becomes approximately becomes an MDP. It is not a real MDP, but like it has all the state has, or in other words, the integrated observation has all the information that is required for you to take action. Is that clear? Any questions? Yeah.
So I kind of understand like some motivation behind the observability, but like the way you designed the Z function, I don't understand why you need an action also to like get the state. Like, why don't you just get the observation just from?
Okay, that's a good question. So why does the Z function has like both? Like why is the Z function? Like I think it's okay. So the Z function is S dash A O dash, right? Like so maybe. Well, I don't know why everybody is using this notation. Maybe it's easier to understand this if I just write this as Z of O dash given S dash comma A. Okay. So the question is, why do we need action as well to estimate O dash? You don't need the action like all the time. Like this is just a general form. Like so, like if you can also just try to learn the mapping from this.
In this example and the grid world, it is like kind of action is redundant, but I'm sure like you have action there, so that means you also have something in mind where the action really matters.
Yes.
For observation. Probably like you can give some example. Like,
yeah. Okay, this is just a general notation. Like so, like it includes situations where you ignore A as well. Okay. So any other questions? Okay, I think there are a couple of questions in the chat. Okay, some questions have been answered. Why didn't we need the history when we use the states directly instead of observations? Okay, so why didn't we need the history when we were using states? It's simply because given the state, I can actually predict the optimal action. Like that's just by definition of a Markovian state, right? Like so the state has all the information required to take the action. On the other hand, like we don't have that Markovian assumption with the observations. So which means we have to integrate information. Okay. So here's the thing. Even for like an MDP problem, okay, like where the state has all the information, sometimes it's a good idea to like use some of the partial observable methods, especially if you're doing function approximation. Okay, the state might have all the information, but your function approximation is erroneous, right? Like so, like you might lose some information because of the function approximation. So sometimes it's a good idea to just look at the history, like even for MDP problems. Okay, now, okay, we will talk about how to do this practically probably towards the end of this discussion. Yeah.
History is like a hyperparameter because we can't store the whole history, right? Like that would be memory intense, right? Like
yes. So well, I think okay. So this is why I said like we will talk about this in okay. Remember your question for end of the topic. Okay, so like so we will talk about like how to do this, like how to model this with function approximation. Like, but for now let's get into the formalism. Okay. Okay. So now, so this is the basic POMDP set. Okay. Now the next question, like the obvious question is like, how do we learn from a POMDP, right? So given a POMDP, like how can I learn an optimal policy, like or how to act optimally in the given world, right? Like so now, as I mentioned before, like it is almost impossible. Like so, like I think in the case of infinite horizon setting, we don't even know if an optimal policy exists. Okay, it's in POMDP. Okay, but there are some guarantees for the finite horizon setting. Okay, but in general, this is an intractable problem. Now, how do I make it more tractable? Right, like so, there are few approaches in the literature. Okay, so one thing that I should say is like the literature for POMDP is not that extensive as literature for MDPs. Okay, so like it's a very hard problem. There's not a lot of progress like MDP. Like so, that's one of the reasons like why you don't see a lot of POMDP work, like even in the deep reinforcement learning era. Okay, we are going to see one most common approach for solving POMDPs, which is the idea of converting the POMDP to a belief state MDP. Okay, we are going to take a POMDP and convert it into a belief state MDP. We'll talk about what is belief state MDP. Okay, so but what we already know is it's an MDP, right? Like so once you convert from a POMDP to belief state MDP, you can easily extend policy iteration, value iteration, policy improvement, like everything to this belief state MDP. Okay, now there's a catch. We'll talk about the catch like after introducing belief state MDP. First, let's talk about belief state MDP. Okay, now a belief state MDP is a fully observable MDP. Okay, it's not partially observable, like it's an MDP. Okay, now this MDP is going to have, it should have a bunch of states, actions, reward function, and everything, right? Like so, now the states in reward, states in the belief state MDP is going to be B, okay, which is all possible distribution of beliefs over the states. This is a probability distribution over the state. Okay, imagine the underlying MDP had 100 states. Okay, now each state of this belief state MDP is a vector of size 100, which sums up to 1. Is that clear? So this is the agent's belief about which state it is currently in. Okay. Now this is a continuous state. It is not, even if the underlying MDP has discrete state space, belief state MDP has continuous state space. Okay, so let's take a simple example. Like, so let's say there are only 3 states in the underlying MDP. Okay, but we are in a partially observable setting, which means I don't have access to these states. Now, a belief state MDP is going to have a bunch of states which are all probability distribution over the 3 states. Like, so for example, like B1 could be 0, 0.5, 0.5. Okay, this is one state of my belief state MDP. This state means that there is a 50% chance that I'm at state 2, there is a 50% chance that I'm at state 3. And I could have a B2 which is 0.9, 0.05, 0.05, and so on. Okay, this is actually a simplex which has all possible probabilities to be in different states. Is that clear? So now you can already start seeing the catch. So belief state MDP is like so huge, like it's going to be computationally very expensive to do things in belief state MDP. Okay, so nevertheless, this is one of the ways in which we can actually solve the problem. So we have to trade compute here. Now, the set of actions is actually the same as the original MDP, or original POMDP, which is same as the set of actions in the original underlying MDP. Okay. Now the reward function, okay, is going to be something like RB. Okay. Now this reward function takes a belief, an action, and gives us some real value. Okay. Now the original reward function that the underlying MDP is giving is for taking an action in a particular state, right? Now we don't know which state we are in, so which means we have to integrate over this uncertainty. So my reward function RB of B comma A is going to be summation over S belonging to capital S, okay, B of S, R of S comma A. Is that clear? My reward function is actually like, given that I am in this belief state, I take an action. Now, what is my reward function? Now, that is just expected value of the reward, like condition on this probability distribution over the states. Okay. Now, there is only one thing left for the MDP. What is it? What else do I need to define the MDP? The transition function, right? Now, the transition function is again have to be modified, because now we are going to talk about transitioning from one belief to another belief, not from one state to another. Okay, this is a bit involved. So the transition function takes a belief, an action, and gives us a belief. Okay, now this function is given by BAB dash. Okay, and this is just the probability of B dash given B comma A. Okay. Now, I can write this as summation over all possible observations. Okay. The probability of an observation given A comma B. Okay. The probability of B dash given A, B, O. See, I have to somehow compute these probabilities from the original POMDP probabilities. Okay, so like we are going to derive TB from the original T. Okay, so this is how we are going to do it. So how do I go from B to B dash, right? So there are like from B, like from my current belief, I get an observation, and after this observation, I'm going to update my belief to B dash, right? So this includes these two probabilities. Is that clear? Any question?
Does the agent need to know all the states to construct the belief?
Okay, so I think, okay, I already saw this question in the chat. So somebody has asked the same question. So does the agent need to know all the states to construct the belief state? Okay, well, of course, it is not possible in many situations, right? Like, so in some situations, yes, but in some situations you cannot. So then you have to even approximate the function, how your belief function is going to be.
So the dimension of belief changes as it learns.
Well, you could also have a different representation, like, but the dimension is not same as the number of states, right? Like, so you can have a function approximation. Then, like, you are in this abstract belief state, like, so, like, where you don't even you can't even count things. Okay, but I think, yeah.
Sorry, if there is some state or factor that you don't know at all in your belief representation, then this belief state MTP will break because you don't ever have a belief to that factor at all.
Okay, can you repeat?
Yeah, if there is a factor in this partial observable and DP that you don't observe and you don't know, like the agent don't know at all, so it doesn't assign any belief to it. Like it is not included in this belief representation. Then we'll, in this situation, this.
Yes. Okay. I get your question. The observation is, if there is some factors in the world that the agent doesn't believe in, then the MDP assumption will break, right? Is that the question?
Yes.
Yeah, that is true. So I think when you develop these belief states, like, so you would normally try to have a non-zero probability over like everything, like, so, like, but it is true that, like, if you don't capture anything, then the MDP assumption breaks. Okay, but we don't need to worry too much about that, like, because when we start developing practical algorithms, you will see that even though, like, we have this framework, like, we will do a lot of approximation. That, like, there's going to be a lot of like errors due to the approximation. So this is not a serious concern. Okay. There's a question in the chat. How do we know the mapping between belief state and observation? Okay, that is what we are going to do now. But probably, given that there's only 1 minute left, like, so we can take a break here and continue at 10:30. Like, so we are still not done with the representation of belief state MDP. So, like, we have to somehow compute these two entities from just what we have access to. Okay, so we are going to do that after the break. So let's take a 10-minute break.